Hi guys, in today's lecture we will understand certain basic concepts that we must know before we start the main memory mapped register programming model as part of the ARM Cortex series microcontrollers. So in today's lecture I will look at certain basic concepts which will help you understand the main memory map programs when we will get into the labs. So concept number one, let us understand the meaning of the word memory space. So let us take a very simple example. If I have a microcontroller which has a 4-bit address bus, means there are 4 address lines here. So the range of address or the range of addresses can go from 0000 to 1111. So in totality we can access 16 different locations. Similarly, if it's 5-bit, then you'll have 32 locations. If it's 8 bits, then you'll have 256 locations, which will go from 0 to 255. So memory space means the total number of accessible locations, the total number of accessible locations. Now please understand, locations does not mean in bits or bytes, they are just locations. Now each location itself can be either 1 byte or 2 bytes or 3 bytes and so on. It's just the total number of accessible locations. Now continuing that example, if we say it is an 8-bit address space such that each location is 1 byte, then we can say that the total address capacity or the total memory capacity is 256 bytes. This is 256 locations multiplied by 1 byte each. Similarly, if you have 10 bits address space, so then you will have 2 raised to 10, which is 1 kilo. 20 bit would be 1 mega and 30 bit would be 1 giga. So if I take a microcontroller which has a 32-bit address space, then what I have here is 30 bits is 1 giga, hence 32 bits will be 2 raised to 2 multiplied by 2 raised to 30, which is 4 giga. So my address space, again I'm saying my address space is 4 giga locations. And if each location I assume is 1 byte, then my total address space is 4 giga bytes. I hope this is clear, the concept of address space. Now, the second concept that we must understand is the concept of memory map. Now, if you look at the typical word map and if you draw a city, the map of a city, you can say that this region of the city is one suburb, then another region is another area, another region is another area. So similarly, when we say memory map, and again let me take the 4-bit address space example. So I would have 16 locations from 0000 to 1111. Using the map analogy or example, I can say that location 0000 to location 0100 is meant for program data. Then from 0100 to, let us say, 1000, this region is meant for code. Then from 1000 to 1111 is meant for some special purpose registers, and so on and so forth. So again, this is a very simple example that I'm taking, but what I'm trying to say here is that each region of memory is given a particular special part to play in my entire system. So this concept is called as memory map. So again, what does memory map mean? It means each region of my address space. We just discussed address space a couple of minutes ago. So each region of my address space is allotted to a particular functionality. I hope this is clear. This example will get clearer once we see the memory map for the Cortex M0 that we are going to study. So the concept of memory map and address space has been discussed. Now let us look at the next concept. Before that, I'm sure you must have seen the lecture on basics of SoC, where we have the microcontroller element and then we have different interface ICs like ADC, DAC, then you have USB, you have UART, so and many more. Now in a typical SoC, when the power is switched on, all the interface ICs are sleeping. Means they are neither given power, and more importantly, they are not given clock. Now clock is a very significant role here. Before that, I'd like to mention that the clock component on the SoC has already been woken up, since the clock module has to supply to the microcontroller. However, the clock inputs to the interface ICs have not yet been activated. The reason behind that is clock is one of the major contributors towards power consumption on a chip. So if you don't supply clock to any interface ICs, that will obviously consume less power. So initially it's only the microcontroller, the clock and the memory that are awake, and the interface ICs are sleeping. So in our example, if we want to wake up any component or the interface IC, then we need to supply clock. And how does that work? Let us see. So let us say this is my ADC, and this is the clock terminal. So outside the clock terminal there is an AND gate with one terminal connected to the clock from your clock module. So this is your clock module, and the other is what we call as a clock enable, such that if clock enable is 0, then whatever be the value of clock, the output is always 0, hence this ADC does not get clock. However, if we do have a 1 at the input, then if clock is 1, then this value is 1. If clock is 0, then this value is 0. And so now clock is actually supplied to the ADC. This concept of using a clock enable and an AND gate is called as clock gating. Means you are putting a gate at the input of the clock terminal to any interface IC. So unless I do not give clock enable, there will be no clock supplied, hence this ADC will continue to be asleep. When I supply clock enable, then there is clock available, hence that time the ADC wakes up. I hope this concept of clock gating is clear. The same concept will apply to all the interfaces on the chip. Interestingly, inside your ARM Cortex M0, now I am speaking with respect to the ARM Cortex M0, you have various ports on your chip. Port A, port B, port C, and so on. Even these ports are sleeping initially, and only when you decide to wake up any of these ports, you must supply clock to your port which you choose using the same clock gating concept. So now it is also applicable to the interfaces and also to the ports of your microcontroller. So whenever we do interfaces or we do ports, we must understand that the first thing we have to do is provide clock so that these guys can wake up from sleep. Alright, so that discusses the concept of clock gating. Now that we've seen the concepts of address space, memory mapped, and clock gating, now let us take an interesting example to understand the concept of memory mapped programming. So let us say I have my port A here, and outside I have an ADC. So as we said before, to enable the clock, we have the clock gating concept. Now I have a flip-flop here and a flip-flop here, that if I store a value 1 here, then clock can go through. Similarly, if I store a value 1 here, the clock can go through. And if I store 0, then no clock. If I store 0, then no clock. Now let us say that we have a register which is a 4-bit register whose first bit is connected to this flip-flop. Let's call it flip-flop 1 and flip-flop 2, and the third bit is connected to flip-flop 2, This is just as an assumption, and we are taking a very simple case. So let us call this register a system clock gating control. So S stands for system, CG stands for clock gating, which is what we are doing here, and obviously this is to control the clock gating. So let's call this a system clock gating control register. So let us say the second bit is for port B, the first bit is for port A, the third one is for ADC, and for fun's sake, let us say the fourth one, or the MSB, is for UART. Now, if I have an application where I want to enable just the ADC and nothing else, then I will store the value 0, 1, 0, 0. Am I right? Because we are just wanting to enable this flip-flop such that we can write a 1 here so that this clock can go through. Similarly, if I want to enable just port A, then I will write the value 0001 into this register. Similarly, if I want to enable, let's say, the UART and the ADC, then I would write 1100 and so on and so forth. So this is a register which we have called SCGC, which is System Clock Gating Control. So now let us take an example that I have a register SCGC, then I have another register SCGC2, which is for some other interfaces. Then I have some data registers. So data 1, data 2. So if this is my microcontroller, so how does my microcontroller know where is SCGC1, where is SCGC2, where is data 1, where is, when I say where is, unless I create special wires for each register, will my microcontroller know where each one of them are? The answer is no. But the disadvantage of having a dedicated wire is that as the number of registers increase, so does the number of dedicated wires needed to connect them, and this is not acceptable. So the solution to that is, previously I had explained that if I have an address of 4 bits as part of my memory map, I can allot, for example, location number 0000 for data, location number 0001 for data 1, similarly 0010 for SCGC2, 0011 for SCGC1. So what am I trying to do? Now each location of memory, or rather let me reverse the statement, every register which I need as part of my system, so every register which I need as part of my system now is identified using a memory location. Now who needs to identify? My microcontroller. So if this is my microcontroller and my microcontroller wants to write a value into my SCGC1, in our example where we said the first bit was for UART, the second bit was for your ADC, the third one was for your port B and the fourth one was for port A, the example that I took. So suppose your microcontroller wants to write the value 1100, then as per our example, SCGC1 is located at location number 0011. So microcontroller will, on its address bus, will put out the location 0011, and on the data bus will put out the value which is 1100. So for my microcontroller, it only has to deal with the address and the data. For the next register, again, new address, new data. This concept is called as memory mapped register programming, where each register of my microcontroller system is mapped to one location on my memory. So one single register has one memory location. So for my microcontroller, it is very easy, as it is always just writing into a memory location and is not worried about the details of the register. So let us go a little bit deeper into how this must be working. So this is my microcontroller. When my microcontroller writes the address 0011, at that time, for every address there is a big decoder which will take the 0011. It will take the 4-bit address, and since it will be a 4-bit, so there is a total of 4:16 decoder, where each line is an enable. So the line of 0011 will give an output 1, and this is your SCGC register. Now every register has two terminals. It has a clock terminal and it has a data enable called as DE. So this enable will be connected to the 0011 because the SCGC register, which is the SIM clock gating, and we've named it as SCGC1, is connected to 0011 as per our memory map. So the data which I want to program as per my example is 1100. So the data 1100 will get loaded onto SCGC1 through the data port. So the decoder takes care of the enable. So as only when enable is 1, that's when the data gets logged on to the SCGC, or any register rather. So this concept of data enable and clock applies to any register. So then when we put 0011 on the address bus, it gets decoded, the data enable is then generated, and the value 1100 is written into the register. So this is to give you a rough idea of how memory mapped register programming works. So at the end of the day, all the microcontroller is concerned, and when I say the microcontroller, it is you as the programmer. All you are concerned with is memory locations. So what we need to understand before we start programming, we need to understand who are my important registers, where are they located, how should I configure them, how should I or rather, let me correct here. What data should I load into them so that I can do something interesting? All right. So all of this information, we have to go and check the architecture, the memory map of my microcontroller, which in our case is the Cortex M0, but the same concept will apply to other ARM Cortex M series microcontrollers. And this is given by the data sheet of the chip manufacturer, which in our case could be the Freescale KL25Z chip, or for a future purpose you could, even if you're using the PSOC 4 chip. So I hope that the concept of memory map register programming was clear. Now the same example, when we will be looking at the ARM Cortex M0, we are now looking at a 32-bit microcontroller. Hence our address space is 4 gigalocations, and since each address is 1 byte, so we will say we have a total address space of 4 GB. So the memory mapping for your ARM Cortex M0 is as follows. So again, this information is provided by ARM. Here, let us start from the scratch. So as per ARM, from location 000 to location 1FFF, again please understand this is 32-bit address space, so this is a 8 location, so 32-bit is total of 4 bytes. So as part of my address space, since it's a 32-bit address space, you will have 8 4-bit hex digits. So there, when we take it from 000 all zeros to 1 all Fs, this is actually 0.5 GB or 500 MB. So 500 MB of the space is reserved. Please understand the concept reserved. Reserved does not mean actually there. Please understand that reserved does not mean actually there. It is just reserved. Then the other 0.5 GB is reserved for SRAM memory. When I say reserved, what we mean is that if you want to connect the part of memory, please understand my statement very carefully. If you want to connect part of my memory where I will be storing code, then as per ARM, you must be connecting the code memory at these addresses only. So if you want code memory to come between address 0x4 all zeros somewhere here, suppose you want to put your code memory somewhere here, ARM says that that is not allowed, because the part of your memory map, what we are looking here, we are looking at the memory map of ARM Cortex M0, and there it says that the first 0.5 GB is exclusively for code. Then the next 0.5 GB is if you want to connect an SRAM memory. Then your next 0.5 GB addresses are reserved for your peripherals. which includes your GPIO and also your SCGC, which is, if you remember what I said, that the system clock gating control register, there are multiple such registers. So you'll have SCGC 1, 2, 3, 4, 5, 6, of which in our first lab we will be looking at SCGC 5. And as per the manufacturer, which is Freescale Semiconductors, so Freescale Semiconductors has told us that, look, ARM has told me to put peripherals from this address to this address, between these addresses, of which I am putting SCGC 5 at location number 4004 8038, and I am putting my general purpose ports, which is your port A, port B, so on and so forth, between addresses 400F F000 and 400F FFFF. So this information on the right hand side is given to us by the manufacturer. These regions here on the left hand side are given to us by ARM. Please understand, this is just the reservation as per ARM, but on the right hand side what we have here is the actual allotment by Freescale, who's the chip manufacturer. So let us understand that here the code memory which ends at 1 FFFFF and the SRAM that starts from 20000, SRAM has been allotted and split into two parts. SRAM is a type of fast memory, just for your information. So what Freescale has done, it has given a certain section of fast memory, fast SRAM memory, to be part of your code memory, and the other part, which starts from 0x20 to 0x200 to FFF, which is this part of this space, for regular SRAM, which is not for code. So let me revise once again. Please understand this, that although the address space for SRAM is 0.5 GB, which is 2 all zeros to 3 all Fs, Freescale has actually given SRAM only from 2 all zeros to 2 to FF. So the address space given to us by ARM is 0.5 GB, but the actual SRAM is not as much. So it is always a good practice to see what is the actual allotment versus what is reserved, and this will vary from chip to chip. So we need to make sure that we are doing that. So this ends our first lecture on basics of memory mapped and how memory mapped works. So before I leave you all, let us quickly understand how things work in memory mapped. So let us say I want to configure my GPIO. So my microcontroller will look for this address, and whatever are the values that you need to write inside the SCGC. So my microcontroller will say at address 4004 8038, please write value so and so, and that automatically gets written into the register using the concept that we understood here, that you have a decoder and then you have a data enable for the register, and that's how it goes. So this is the basic concept of memory map register programming. In the next lecture, we will understand a few more details on how to actually configure registers and do the memory map programming. Thank you.